Are you recording? Okay, right. Yes, now Kim and I are going to talk to you about Swift and how to do Swift data analysis. But first of all, I'm going to give you an introduction about the satellite and the instruments and what it can do. So Swift was launched on November the 20th, 2004. And as I'm sure you're aware now, the main goal was to monitor gamma ray bursts. So it was launched on the Delta rocket you can see on the left. We were quite lucky in that they put a camera on board inside the fairing at the top there, so we could see the satellite being ejected from the rocket as it was launched. But it was a very poor video link at the time. That was over 20 years ago. On the right-hand side, you can see what Swift looked like when it was in the clean room at Goddard. And for scale, there are a few people on the platform by the bat. So the bat is the grey instrument there on the top of the satellite. So at launch, its nominal lifetime was only 2 years, with an expectation it might go to 5 years. But of course, we're now 21 years later nearly, and it's still operating, which is great for us. It keeps us employed. Some minor facts about Swift. As its name suggests, it slews quite rapidly. Quite unusual for an astrophysical observatory. So it slews about 100 times every day. Sometimes to follow new targets, sometimes just to keep the XRT cold when we can't observe, when we're in the South Atlantic anomaly. And we worked out recently that Swift has orbited the Earth about 115,000 times since launch. So if we look at the instruments, you've heard that there is the Burst Alert Telescope, which is the hard X-ray detector. It has approximately 2 steradian field of view, which is about same visibility as a human.
One eye.
One eye. And few arc-minute accuracy. When it detects a new burst, it can record the position within to a few arc-minutes accuracy. So that's the Burst Alert Telescope, the BAT. Then we have the X-ray telescope, which is the soft X-ray instrument, 0.3 to 10 keV. And when the XRT gets onto the target, it can it has a field of view of 20 arc-minutes, and it can detect the source within about 3.5 arc-second accuracy, or that can be improved because we can use the UVOT as a superstar tracker and get better positions. And on the left there, the bottom left, the box shows UVOT, which has UVV and UV filters and optical prisms. So that can localize the source to within sub-arc-second accuracy when we start observing GRB. So Swift operates autonomously. So it decides when and if it can slew and how it can slew if the bat triggers. So there are times when we might not be able to slew if the Earth is in the way, or the sun is in the way, or the moon is in the way. And it has to then decide what path to take around the sky to get to the new target. And it's just that all automatically. So the bat and the XRT and UVOT can get prompt data telemetry to the ground, which is when you receive the first burst alert from the telescope. So the bat will send down the light curve, the XRT will send down the position and the light curve, and the UVOT can also send down the position.
I have to stop you, sorry. I noticed that from online, they see the presenter mode.
Oh.
So the only problem is that they miss the very bottom of the slide.
Okay, how do we fix that?
Yeah, only the very bottom.
So yeah, actually they are seeing this.
Is there a presenter mode then? Not full screen.
No, that's not. I don't know. I just went to presentation. It's a PDF, so I.
Try again.
It's so.
Yes.
Maybe I can share a different bit instead of sharing the whole
share the entire
thing.
screen.
Yeah.
I can share the entire screen. Let's try like this.
So
stop presenting.
yeah, stop presenting. Sorry, guys.
Entire screen 1 or 2. I think that would be the same. Try screen 1. Yes. Select.
Except it's in a different window.
Oh.
Let me try
Okay.
screen
So
2.
screen 2 probably.
No.
No, but try. It should work. I think it should work. Screen 1. Then you have to select it by clicking here.
I do allow. Allow. I'm guessing.
So probably instead of not now, try to.
Needs permission. Let me. Yeah. Okay. But what I actually want. Right.
Okay,
So,
no
but
problem.
that's not sharing.
No.
Um,
Try again on.
so I don't think it can be that
No, I
option.
think it's just instead of not now, there is an arrow there.
No, always
Oh,
blocked.
no, okay, so this.
But no, I think it's.
So screen one.
I mean, the alternative would be to drag it into this one. Hold on, we could try that. Just trying something.
Oh, look, okay, that's perfect.
Um,
And now try to go the full screen or presentation or whatever. And now,
Yay!
Yeah, that's perfect now. Thank you.
Technology, any grade.
Right, where were we? Yes, so Bartex UIDs can send down the prompt GRB data to the ground. We get alerts, often to our mobile phones, like we did during dinner last night. And usually, what's also unique about Swift, you can get the full data set down within a few hours. Most telescopes, you have to wait for weeks or months to get the data available. But also, the Swift data are public immediately, so anyone can look at them. So the BAT itself is the hard X-ray imaging telescope. It can image over the range 15 to 150 keV. It uses the coded mass technology, which has a mass with an array of 1 millimeter lead tiles with a 1 meter focal length. And there are over 32,000 CZT detectors underneath these tiles. So when a GRB or a new source is imaged by the BAT, it projects an image of the mask onto the detector plane, and by some fancy data processing, you can reconstruct the image and the position of the object. What's the status of the BAT? It's operating well at the moment, nominally. Typically, at any one time, there are somewhere around 15,000 detectors enabled, and others are disabled due to noise. But the BAT team are continuously adjusting which ones are on and off, because some get better, some get worse. It was launched with 4 redundant loop heat pipe controllers, which help keep the BAT cool, and 3 of the 4 have actually failed, but the 1 remaining controller is sufficient for its thermal requirements to keep it operating. The XRT. So the XRT is a traditional Volta Type 1 mirror. This was actually a JetX flight spare. JetX was a mission which never launched, and it was built here, actually, in Milan, in Milano. It combined with an E2V CCD22 detector, which is the same as flown on the XMM MOS cameras, so it's actually one of the MOS flight spares. And it's sensitive over the engine rate 0.3 to 10 kV. So on the top right graph there, it shows the combined mirror and filter area, filter transmission function. So and the bottom graph shows the QE of the detector. So these two, the mirror area and the filter transmission get put into the ancillary response files, the R files, which are used for spectral fitting, and the QE is built into the RMS, which are used for spectral fitting. So these two are combined. If you plot effective area and X-ray, you see the combination of those two things. So XRT continues to operate well. We've had no new anomalies for a while, so we have rebooted spontaneously in the past. We get multiple bit errors in the electronics, but we haven't had one of those since 2016, which is quite unusual because we get them quite frequently every couple of years. One thing that did happen shortly after launch, the XRT had a thermal electric cooler to keep the CC cold, but it actually failed. The power supply unit to it failed. But by carefully keeping the XRT radiator pointing into deep space most of the time, we can keep the XRT operating below -50 to around -65 or even -70 degrees Celsius. So that's all thanks to the science planners. And the bottom shows a couple of our calibration sources. On the left is the Tycho supernova remnant, and on the bottom right is the Casset supernova remnants. We use those for game calibration purposes. So XRT has a number of modes, actually. When the BAT triggers, we slew. It takes 60 seconds, maybe 2 minutes to get on target. Then we operate in what's called imaging mode. This is like operates as a normal optical CCD. It just integrates in low exposures, like 0.1 or 2.5 seconds. And that is sufficient for a bright thing such as the GRB to get a position usually. And Then it was intended that we would go into this photodiode mode, which is a non-imaging mode, which just reads out the CCD very quickly, because we need to avoid pileup. Because when CCDs are operated in photon counting mode, ideally you want to detect 1 photon per pixel in each frame of data. And if you get more than that, you can get pileup. So photodiode mode, unfortunately, we had to disable it quite early on because the CCD was hit by a micrometeoroid. And it caused hot columns on the CCD, which have to be blocked out, but they can't be blocked out in photodiode mode, so we have to disable that mode now. The 2 modes you'll most likely care about are window timing mode, which is used when the count rate on the XRT is above about 2 counts per second. It's used to avoid pileup. It's one-dimensional imaging, and it has about a 1.7 millisecond readout time. Then the other mode is photon counting mode, which is a more traditional 2-dimensional mode with a 2.5 second time resolution. So it automatically, when we get on the target, the XRT goes through the imaging mode to get the location, then it switches to window timing mode, and if it stays in, if it's bright enough, it'll stay in window timing mode, but if it gets below 2 counts per second on board, it will drop into photon counting mode to track the GRB light curve as they evolve. And the UVOT is a 30 centimeter telescope. It can perform imaging and prism spectroscopy over the 170 to 600 nanometer waveband. It's actually a micro-channel plate intensified CCD detector, and it has an array of UVB and UV filters, and the figure on the bottom there shows the schematic of the filter wheel. Because it's a micro-channel plate intensified CCD detector, it can actually suffer from something called coincidence losses when the optical target's quite bright. So we tend not to observe bright targets with the UVOT. Was it about 8th magnitude?
No, well, yeah, anything that we can't observe anything brighter than 6 magnitude,
magnitude.
because that would actually damage the CCD.
So we tend to look at the targets when they're fainter than that. So this shows the UVOT filter response curves here. So one important thing to note is that the UVW1 and the UVW2 have what are called extended red or long wavelength tails. So they can be contaminated by the source optical emission rather than just be UV emission. But the UVM2 filter does not have these long tails. And also shown there is a white broadband passband, which is quite often used in the early stages of GRB detection. One thing you may have heard recently in the news is that this thing about the Swift orbit boost. So solar, initially when it was launched, we were about 600 kilometers in altitude and a 95-minute orbital period. But this solar maximum has been quite bad for Swift, because when the sun is active, it bloats the Earth's atmosphere and it causes more drag on the satellite. And right now, the altitude is somewhere below 450 kilometers, I think. And
The mean is 450.
the mean is about 450. And right now, it's predicted to re-enter towards the end of next year. But there's been this press release recently that NASA have contracted a private company called Catalyst Space Technologies to build a probe to catch Swift and give it an orbital boost. Now, this is unproven technology, but we are here operating with our fingers crossed for the next few months, hoping they succeed. I think they're going to attempt to do this in May and June of next year. So this is figures from the press release from the Catalyst Technologies website. We hope they don't damage the XRT, which is sticking out from the bottom of the Swift, which is there, as well as the antenna. But hopefully they're aware of these things, and we hope that will be successful. Okay, I think it's going to be.
Yes.